For this warm-up, we're going to figure out the domain and range of these functions. So for this quadratic function, we know that the domain is going to be any real number, no restrictions. For the range, we have to look at two things. We have to look at this c value and this a value right there. So based on those two pieces of information, you can say that our range is going to be any real number such that y is less than or equal to 2. So less than or equal to because of that a value. And the 2 is because of our c value. For the next function, we have a root function. Now what I'm going to do first is I'm going to write this in factored form. So I'm going to common factor out the negative 2. So I get x plus 6 underneath the root, and then I get the plus 3. So that'll allow me to properly state my domain is any real number such that x is less than or equal to negative 6. So I know that it's less than or equal to because of this negative here. That's what affects my my x values being smaller than or equal to. So I have a largest possible x value, and that largest possible x value comes from my translation 6 units to the left. Okay, x plus 6 means 6 units to the left. So I'm starting at negative 6, and my x values are all smaller than that. So I write down my domain as any real number, x less than or equal to negative 6. And then for the range, it is any real number such that y is greater than or equal to 3. And 3 comes from, again, my c value here, translation 3 units up. And then for my last rational function, my domain is going to be my restriction in the denominator of this rational, x minus 14 over 3 when I factor out that 3. Okay, so then I'm going to say that x can be any real number except 14 over 3. And that's actually the location of my vertical asymptote as well. And for my range, I'm going to write down that y is any real number except positive 2 over 3. Okay. Okay. So now what I'm going to do in the next part of this exercise is I'm going to take each of these functions and I'm going to reflect them in the x-axis. So remember, to reflect in the x-axis means that I am going to take my functions and I'm going to change them into negative f of x. So this means that I'm going to multiply all of the terms by negative 1. That's what it means to reflect a function on the x-axis. Okay, so let's take our f of x, which is originally negative 3x plus 3 squared plus 2, and I'm going to take this and I'm going to apply the negative in front of the function to show that it's been reflected on the x-axis. And then what I'm going to do with that negative is I'm going to very carefully distribute inside my square brackets. So then my overall function without the big square brackets is 3x plus 3 squared minus 2. So the original function was opening down and had a vertex of 0, 2. After the reflection on the x-axis, it's now opening upward and it has the vertex at 0, negative 2. Okay, so I'm going to do the same thing to my g of x function as well. So I'm just going to copy down to start with. G of x equals root negative 2x minus 12 plus 3. And now I'm going to just put square brackets around everything. And I'm going to put a negative in front to show that I've reflected on the x-axis. And again, I'm going to take that negative and I'm going to distribute. So then I end up with negative square root negative 2x minus 12 minus 3. That would be my final g of x function that's been reflected on the x-axis. Okay, and then my last example is h of x, which is equal to 5 over 3x minus 14 plus 2 over 3. Again, I'm going to put square brackets, and I'm going to multiply the entire function by negative 1. So I'm going to distribute my negative. So I have negative 5 over 3x minus 14, and then minus 2 over 3. Okay, so essentially what this means is if you are reflecting in the x-axis, then you're affecting your a value and your c value. Okay, a and c. A and c. Okay, but your b and d, your horizontal stretch compression factor and your horizontal translation factor, does not get affected when you reflect on the x-axis only. So now for the next part of this warm-up, we have the reflection in the y-axis to take care of this time. So when you are reflecting in the y-axis, this means that you want to change f of x to f of negative x. So what that really means is you should be replacing all of your x's with negative x, and that takes care of the reflection on the y-axis. Let's start with the first example. We have f of x equals negative 3x plus 3 squared plus 2. But what I want to do is, instead of f of x, I want to replace the x's with f of negative x. Negative x. Okay, so then that means that f of negative x will be negative, in this case, negative 3x plus 3 squared plus 2. Let's continue with the next example. So we have g of x equals square root of negative 2x minus 12, and then plus 3 on the outside. But once more, we would like to replace our x with negative x. So that'll give us square root of 2x minus 12, and then plus 3 on the outside. Okay. And then for our final example, we're going to have h of x equals 5 over 3x minus 14 plus 2 over 3. And again, we want to take our x and replace with negative x. And then that will give us h of negative x as 5 over negative 3x minus 14 plus 2 over 3. So in this case, when we reflect on the y-axis, our a and c values, a and c are unaffected. It's actually our b and d values that do get affected. Okay? Take, for example, here, the original g of x used to be reflected on the y-axis, and then when you factored out the -2, it would have been translated 6 units to the left. But after we reflect that original function in the y-axis, we end up not having a reflection and instead translating 6 units to the right. For the last example, if you want to reflect a function in both the x and the y-axes, what you want to do is change f of x into negative f of negative x. So you want to do both of the replacements of x with negative x, and also multiplying all of your terms by the -1. So what I would recommend is either take your answers from part A or part B, and then just add in the other reflection, okay? So in my case, I can't really see what I wrote down in part A very well, so I will just work off of what I have in part B. So I already have f of negative x is equal to negative 3x plus 3 squared plus 2. So what I'll do is I will take that function that's already been reflected on the y-axis, and I will multiply everything by -1 so that I can have the reflection on the x-axis as well. Okay, and then I'm going to take that negative and I'm going to distribute it properly. So I end up with negative f of negative x equals bracket negative 3x plus 3 squared minus 2. And I'm going to repeat that with g of negative x. It's square root 2x minus 12 and then plus 3. But again, I'm going to reflect on the x-axis so that I will end up with negative square root 2x minus 12 and then minus 3. And my final example, I have h of negative x is 5 over negative 3x minus 14 plus 2 over 3. Again, I want to take everything, multiply by negative, and I end up with negative 5 over negative 3x minus 14 plus 2/3. And if you notice, there's a lot of negatives here in this rational expression. So I'm going to actually cancel out all of these negatives. Okay, essentially I'm common factoring -1 from the denominator and from the numerator, and then canceling out that -1. So my final answer can be 5 over 3x plus 14 and then plus 2 over 3. So that's my final answer for negative h of negative x. And if you ever wanted to check any of your answers were correct, you could always use Desmos, okay? Plug in your function for h of x, for example, the original function, and then replace the x with negative x. See if you do get the correct algebraic model, and then also stick another negative in front, and then compare it with this answer. Okay, make sure that everything matches up. So, for today's part 2 inverses lesson, we are going to work on restricting domain and range of the inverse. And basically that'll help us figure out the inverse function. Okay, so let's start with this example, which we already covered yesterday during 3.8 video. Determine the inverse relation of f of x equals x squared plus 2. So that means that I need to, first of all, rewrite this as y equals x squared plus 2. Then I'm going to switch x and y like so. And then I want to work on isolating for this new y. So I have x minus 2 equals y squared. And then I'm going to take the square root, but because I'm going from square to square root, I have to put the plus minus in front. Okay? And we for sure know that this is a relation, not a function, because of this plus minus in front. That produces two y values for every x value, right? So let's just write that down. This relation is not a function. Every x produces two y values because of that plus minus. Okay. However, if you look at the inverse relation separately as two separate branches, okay, then that means that we could write this as the first branch, y1, as positive root x minus 2, and then the second branch, y2, as negative root x minus 2. And each branch, y1 and y2, would be a function on its own. So what that really means is we can restrict the domain of the original function so that the inverse will also be a function as well. Okay? So what that means is, right now, looking at this original function, f of x, we know that the domain is x is any real number, right? No restrictions, which leads us to having this range for the inverse being y is any real number. Okay? What we want to do is we want to restrict the domain of the original function. So we want to change the domain, change it to something else other than any real number, so that this range will change, so that we won't have this plus minus in front. We'll either have just the plus or just the minus, which on their own would mean that y1 by itself or y2 by itself would be the inverse function, not just a relation. Now we're going to look at how to restrict the domain of the original function so that the inverse will be a function as well. So my parabola is translated 2 units up. So it looks like this. Okay. Now, what I want to do is I want to restrict the domain of f of x equals x squared plus 2 so that only one branch of this parabola exists. Right now there are 2 branches, 2 arms, okay? I want to get rid of either the left arm or the right arm, doesn't really matter which one. Let's just get rid of the left arm, why not? So that means I want to somehow delete this left arm from existence. So in order to do that, I'm going to restrict the domain of my parabola so that it's any real number greater than or equal to 0. Now, why did I choose 0? I chose 0 because that is my x coordinate of the vertex. Okay, so that essentially guarantees that I only have the right arm of the parabola left. Okay, and in that case, if I just have this right arm of my parabola, then when I take my function and I reflect it on the line y equals x, because that would be how I get the inverse function, then all of a sudden my inverse is just going to be this top arm of my root function. Okay, so the inverse will only be the positive root function translated 2 units to the right. Okay, essentially this first y1 branch that I had written up here. Okay, with this point, starting point being at 2, 0. Okay, and what that means is now the range of the inverse function is not any real number anymore like it used to be. It's now going to be y is a real number such that it is greater than or equal to 0, because it's just the domain of the original function, right? This domain becomes the range when you take the inverse. Everything switches, right? That's what we discussed yesterday. So this is essentially what you need to do anytime you start with a parabola as the original function. Okay, you need to delete one arm by putting a restriction on the domain. Okay, and again, I deleted the left arm of the parabola so that I deleted the negative branch of the inverse. But if you wanted to delete the right arm of the parabola to delete the top arm of the inverse, that would be fine as well. So let's do some practice. For each of the following examples, we're going to determine the inverse function by restricting the domain of the original function if we need to, and then we're going to state the domain and range of the inverse. So when we take a look at this first function, we know that it's a linear function. So for this linear function, I'm going to say y equals 2/3 x minus 4. I'm going to switch x and y like I normally would. Then I'm going to work on getting my inverse by doing opposite operations in backwards order. So I get x plus 4 equals 2/3 y. And now I want to get rid of this 2/3 on the right hand side. Okay, so that means essentially I want to divide by 2/3 on both sides. But it's always confusing when we divide by fractions. So instead, why don't we think about this as multiplying both sides by 3/2, the reciprocal. Okay, because if we multiply both sides by 3/2, that helps us get rid of the 2/3 on the right hand side, because we would have been multiplying by the reciprocal. So reciprocal of 2/3 is 3/2 on both sides. That'll help us get rid of our 2/3 rather from the right side. Okay. And when we take a look at this inverse, we can clearly see that we have another line, a linear function. Okay, if this doesn't look familiar to you, you can just expand, get rid of the brackets, and that will give you the linear function f inverse equals 3/2x plus 6. Okay, so this is the line with a slope of 3/2 and a y-intercept of 6. Okay, that means that we didn't need to do any special domain restrictions for the original function because the inverse was a function itself. Okay, and just for practice, we are going to state domain and range for this inverse function. So our domain is any real number, and our range is also any real number. So let's try the next example. We have a quadratic in standard form. If you remember from yesterday, the first thing that we had to do was get this quadratic into vertex form. So we're going to common factor out half from the first two terms. Please remember that when you do 3 divided by half, it's the same thing as 3 times 2. So that means that you should have x squared minus 6x inside the brackets. Okay. Then I'm going to go right into my completing the square step. So I need to complete the perfect square trinomial. So to create that last term, I need to take the 6 divided by 2 to get 3. And I'm going to take 3 and I'm going to square that number. And because I added 3 squared, I also need to subtract 3 squared. Okay, So I haven't changed the value of anything, which is the whole point of completing the square. Now I'm going to rewrite this as half x minus 3 squared. This is plus half times negative 9 plus 1. And now when I have half x minus 3 squared, this is negative 7 over 2 plus 2 over 2, or sorry, negative 9 over 2 plus 2 over 2, which will give me my final 7 over 2 answer. So this is my parabola, okay, which usually has a domain of x is any real number. But as we saw on the previous page, we encounter a problem with parabola, so we are going to have to restrict the domain, okay? So let's start working on the domain restriction, okay? If you remember from the previous page, in that example, we said x has to be greater than or equal to 0 because that was the x-coordinate of the vertex. So we're going to do the same thing here. We're going to take the x-coordinate of the vertex, and we're going to say that our domain restriction is that x is any real number, so that x is greater than or equal to 3. So essentially what we've done is we've taken this parabola and we've deleted, again, the left arm, okay, so that the parabola starts at 3, negative 7 over 2. Okay. So now that we have this, we can work on getting the inverse. We have x and y switch places, like so. And now we work on isolating for the new y. So first I'm going to add 7 over 2 to both sides. And in my next step, I'm going to divide by half. But again, I don't like to divide by fractions. I would rather multiply by the reciprocal. So I'm going to multiply both sides by 2 over 1. Okay. So when I do that, I get 2 times x plus 7 over 2 equals y minus 3 squared. Okay. When I get rid of the brackets, I get 2x plus 7 equals y minus 3. I'm going to take the square root, and for now I'm going to put the plus minus, okay, just to show that I really do understand that when I go from square to square root, that I have to put the plus minus there, okay. And then my final step, I'm going to take this and I'm going to add 3 to both sides. Okay, but because in the original function we restricted the domain, I can now say that the inverse function should be simply root 2x plus 7 plus 3 without the plus minus in front. Okay, and I'm going to write down that my domain and range is x is any real number so that it is greater than or equal to negative 7 over 2, and the range is simply the domain of the original function. So I'm going to write y is any real number so that it is greater than or equal to 3. Okay, in my next example, I'm starting off with a root function. So I'm going to just work on y equals 2 root 3x plus 21 minus 4. I'm going to work on getting the inverse. So I'm going to switch x and y. And then I'm going to work on opposite operations in reverse order. So I'm going to add 4 to both sides. Then I'm going to divide both sides by 2. Or if you would like, again, talking about operations, inverse operations, instead of dividing by 2, it would be the same thing as multiplying by half. So I'm going to write this as half x plus 4 equals root 3y plus 21. Now, you have to be a little bit careful here. What's going to end up happening is we are going to square both sides of the equation to get rid of the square root. Okay? So let's finish off. We have half x plus 4 in brackets, all of it in brackets, squared minus 21 is equal to 3y. And then for our final step, we're going to divide every term on both sides by 3. So that means we're going to divide this by 3, we're going to divide this by 3, we're going to divide this by 3. So then that gives us our final algebraic model of half x plus 4 squared over 3, but instead of over 3 again, I'm just going to put it in front as 1/3 minus 7 equals, and now I'm going to say right away that this is a function, and I know that this is a function because I see the square. It's a parabola, okay? But what I want to make sure you understand is that the domain and range is not necessarily what you think it is for this inverse parabolic function. The domain is not x is any real number. It's actually going to be x is greater than or equal to -4. Okay, and the reason for that is because if you take a look at the original function here, our domain was x is greater than or equal to -7 xer, and the range was y greater than or equal to -4 yer. Okay, so this domain and range makes sense based on the fact that this is a root function. So when we take this root function and we change it to its inverse, okay, we do get a quadratic because this is now degree 2 square, but the domain of this quadratic is not just xer, it's actually the old range of the original root function. So it does naturally have this domain restriction that x has to be greater than or equal to -4. So don't forget that. So essentially what I'm saying is when you think about the graph of this original root function and its inverse, we're going to end up getting what looks like this, -7, here at -4, and this was the root function, like so. Okay, and then for the inverse, we are now going to end up getting, this is -4, and this is -7 here, and we get something like this. Okay, so we only get the half of the parabola, not the full parabola. Okay, so the domain is x is greater than or equal to -4, any real number, and the range for the parabola would be y is greater than or equal to -7, any real number. Okay, I just have a tiny little bit of space left for the last example, sorry. So here we go. We are going to, I'm going to just skip right to the step of switching x and y. So I'm going to say x is equal to -2 over 4y minus 12 plus 6. So x minus 6 equals -2 over 4y minus 12. I'm going to multiply both sides by 4y minus 12. So then I end up with 4y minus 12 times x minus 6 on the left side, and I will end up with just -2 on the right side. And that will help me isolate because now I can say 4y minus 12 is equal to -2 over x minus 6. So I can now say that I'll have 4y equaling negative 2 over x minus 6 plus 12. And then I'm going to divide each of my terms by 4. And again, if you don't want to divide by 4, that's essentially the same thing as multiplying by 1/4. So this negative 2 multiplied by 1/4 is going to reduce down to negative half. So then I'm going to have negative 1 over 2 bracket x minus 6 plus 3. And that will give me my inverse function. Okay, started off with a rational function. I end up with a rational function. And sorry, I don't have any room to write it down, so I'll just verbally state the inverse functions, domain and range. So domain is that x cannot equal 6, but x is any real number. And the range is y is any real number except 3. Okay, so the domain and range switched, because in the original function, domain was x is any real number not equal to 3, and the range was y is any real number not equal to 6. You can see how domain and range switch here as well. Okay, and that basically is it for our inverse functions, relations, and properties. So here's some summary of key ideas on this last page of the lesson. The inverse of a function is the reverse of the original. So the inverse will undo what the original has done, and it can be found using the inverse operations for the original function in reverse order. And the whole idea of this, it undoing the original function, is what causes f of g of x and g of f of x to equal x when f of x and g of x are inverses of each other. So we covered that example yesterday in the notes. Okay. The inverse of a function is created by switching the x and y coordinates. That is such an important point, so I'm going to just underline. Okay. And by switching x and y, it results in a whole host of things, including domain and range becoming range and domain, and then also the fact that the graph is simply the reflection of the original function in the line y equals x. Okay, and then the point that I also want to highlight again, the inverse of a function is not necessarily a function itself. Okay, so you should understand that this is a result of the fact that a function needs to have one unique y for every x. This means that a function can have two x values for one y. So when we take the inverse of a function, it may turn out to have two y's for one x, since x and y switch. So this is a very, very important point about functions, why the inverse is not necessarily a function itself, okay? Because if we start off with a function that actually has two x values for one y, which is okay to have in a function, but then we take the inverse, which means we switch x and y, then all of a sudden those two x's for one y actually turn into two y's for one x, which is not what the definition of a function is. Okay, but when that happens, okay, what we just covered in today's lesson is we need to restrict the domain of the original function so that the range of the inverse relation will be restricted, and therefore the inverse relation will actually turn into a function as well. Okay, and just a couple more points. A way to determine the inverse function is to switch the two variables, so switch x and y, and basically when I say solve for the previously independent variable, I'm saying isolate, okay? And when we say isolate for the previously independent variable, that is basically just doing the inverse operations in reverse order, which is what we talked about up here, okay? And then the last thing is, in general, just use y equals for the inverse relation, okay? But if you know for sure that the inverse relation is actually a function, then please make sure to use this f inverse notation. And that's it for the unit. Congratulations, we're done.